This is section 5.1, Matrices and Linear Systems, part 2. In the previous video, we introduced a lot of the terminology for matrix algebra. We talked about matrices, whether they're equal, how to add them and take scalar multiples. And then toward the end there, we introduced the scalar product, also known as the dot product. And we used the definition of the scalar product to then define how to multiply two matrices. In example 3, we saw that the product AB is typically different than the product BA, so matrix multiplication is not commutative. And we ended by doing an example of computing the determinant of a 3x3 matrix by way of cofactor expansion. So this is where we ended, and we're going to pick up here at page 5. We're going to dive into a little bit more of the linear algebra and then talk about how it relates to systems of differential equations. So a few more definitions before we get started. We discussed what it means to be an inverse. That is, when you multiply a matrix A by its inverse on the left or on the right, then you get out the identity matrix. As it turns out, not all square matrices have inverses. So the quickest way to check is to compute the determinant. And if the determinant is non-zero, then we can guarantee that the inverse exists. When the inverse exists, we call that matrix non-singular. So again, all that means is a matrix is non-singular if it's invertible. However, if the determinant equals 0, that's bad, and we say that the inverse matrix does not exist, and in that case, we call it singular. So some more terminology here. We have kind of a quick way to find the inverse of 2x2 matrices. So we're going to start out with matrix A here. And if we want to find its inverse, what we need to do is first compute the determinant. And we want to take the reciprocal of the determinant. And we multiply or scale by that inverse of the determinant. And what we have done here is swapped the places of A and D. So you see those right there. And then we negated the entries B and C. So we see those negative entries there. So let me clear this out just so that we can see it. All right, and so let's just do an inverse matrix for practice. We're given the matrix A. Let's go ahead and find the determinant of A. So that's going to be 2 times 7 minus a negative 3 times 4. So 14 plus 12 for a total of 26. So the determinant is 26. So that tells us that A inverse is 1 over 26. Technically the absolute value of 26, but I'll omit that, times the matrix, where I'm going to switch the entries on the principal diagonal and negate the entries on the other terms. So this right here would be our inverse matrix. All right, this only works for a 2x2, of course. So if you have a more complicated matrix, those issues of finding inverses would be addressed in a full linear algebra course. All right, so we're going to get into how we can utilize matrices in terms of differential equations. And so what might be something that you haven't seen before, even if you've taken a linear algebra course, would be matrix functions. So a matrix function is a matrix in which every entry is a function of t. So rather than just having scalar numbers in every entry, now we're going to talk about having actual functions. And here they're specifying that the independent variable is t. We say that the matrix function is continuous or differentiable if each of its elements has that particular property. And then finally, the derivative of a differentiable matrix is the matrix of derivatives. In other words, you can just look at every single entry, take the derivative of each of those functions, and that becomes the derivative of the matrix. So we have a couple of properties. This first one just says that the derivative distributes across matrix summation. And the second property here says that matrices obey the product rule. So just in thinking about when you take the derivative of the product of two functions, now we're talking about taking the derivative of the product of two matrices. And so you can see the product rule, derivative of the first times the second plus the first times the derivative of the second. So that product rule is just still alive and well here with matrices. So for example 6, we're given a matrix of functions and we want to find the derivative of the matrix. Again, following the definition, that just means that we want to take the derivative in each coordinate. So for the first entry, entry 1, 1, the derivative of t is 1, and the derivative of 2t minus 1 is 2. And then moving down to row 2, entry 1 or column 1, derivative of t cubed is 3t squared. And then of course the derivative of 1 over t is a negative 1 over t squared. So this matrix of derivatives is the derivative of the differentiable matrix. All right, so here comes our information regarding systems of differential equations. We're going to suppose that we have this giant system here. And it's of n first order linear DEs. You'll notice that we happen to have these external functions, which is going to lead us to a non-homogeneous equation. But we're just going to start with this system of n first order DEs. And what we want to do is we want to arrange these in such a way that we can display it as a matrix. And then we can use matrix algebra to simplify this system. So we'll begin by finding the coefficient matrix. So that is the matrix consisting of all coefficients of the xi terms. So we're talking about these p guys, p of t. So I just underlined the coefficients in the xn prime, but of course they go all the way up through the x1 prime. So if we pick off all of those coefficients and we throw them in a matrix, the way you think you would, right? So the P11 of t goes in the A11 entry and so on and so forth, then we're going to call that the coefficient matrix. We can also define the column vectors. So I just want to emphasize that these are going to be a column where x, and it's bolded because it's a vector, so you could put a vector hat on top, is the matrix of, or is the column vector of the xi's. So in other words, we're going to say x is x1, x2, down to xn. And similarly for the f of t external functions as well. Then what we can do is we can write the system in shorthand using this notation. This guy right here is going to be a column vector. This and this is also a column vector. And then this is a matrix. All right, so we're able to condense this somewhat ugly looking system up here to a much more convenient looking matrix setup. Now that we're talking about larger systems of equations, what is it, systems of DEs, what does it mean to be a solution? So if you think back to chapter 4, we were working with systems of two equations, and the solutions were always two functions, generally an x of t and a y of t. Rather than dealing with the alphabet and going x, y, z, and then starting back over, you'll notice that what we've done instead is subscripted them with an x1, x2, x3 out to xn. So now a solution is going to be a column vector function, meaning we're going to have n functions. X of t equals all of these individual solutions, x1, x2, x3 out to xn, such that each component function satisfies the differential equation. Now, if we want to talk about a homogeneous equation, what we're doing is we are, let me clear this off up here. The associated homogeneous equation is, you'll notice that that f of t got dropped. So if we just drop off those external functions, we call that the associated homogeneous equation. All right, so for example 7, what we want to do is just get some practice in writing this differential system in terms of this matrix format. All right, so we have 1, 2, 3 first-order DEs, and I am going to write this in the following way. I'm going to say x prime, y prime, z prime equals, and now I'm going to pick off my coefficients. For x, we have a 2 in the x, a -3 in the y, and 0 in the z. For y, we have 1, 1, 2, and for z, we have 0, 5, -7, and all of this is times x, y, z. Okay. Sometimes you'll see a notation in this format. X prime equals the same coefficient matrix 2, -3, 0, 1, 1, 2, 0, 5, -7 times x, and then they'll define what vector x means, where that is x, y, and z. So 2 different ways to display this depending on whether you want it to be shorthand or not. All right, so that's an example of working with systems and writing them in matrix notation. All right, so how are we going to solve these systems? That's our end goal. So it's going to be very similar to what we've been doing back in chapter 3. Suppose we have n solutions to our homogeneous DE written in this format. Then what we know by the principle of superposition is that we can take a linear combination of those n vectors, and that is in turn a new solution. All right, so how do we get the general solution? You guessed it, we need those vector functions to be linearly, actually, no, we don't want linearly dependent. We want them to be linearly independent. So that's our goal. So first we're defining what it means to be linearly dependent. It means that you can find, or there exists, constants C1 through Cn, not all 0. It's okay if some of them are 0, but not all 0, so that the linear combination of those is equal to 0. This is a bad characteristic to have. As we saw in chapter 3, and we're going to see again here in chapter 5, we really value linear independence, so we hope to not run into linear dependent. If you can't find these coefficients such that they add up to 0, then we say they're linearly independent. Now again, back in chapter 3, we saw where the Wronskian was very important because it allowed us to methodically be able to check whether a set of solutions were linearly independent or not. So first we have the definition of the Wronskian. The Wronskian is just the determinant of the matrix that's composed of all of these xij functions. So it's the determinant of the matrix whose columns, here we go, whose columns are those solutions x1 through xn. So this first row is the column vector x1, the second column is the column vector x2, and the final column is the column vector xn. Okay, all the way over. So this brings us to our next theorem. How can we use the Wronskian to identify whether we're linearly independent or not? And so theorem 2 says the following. Suppose that we have these n solutions to the homogeneous DE x prime equals p of tx. We also want to suppose that that coefficient matrix p of t is continuous. All right, then if we let W represent the Wronskian, if x1 through xn are linearly independent, then the Wronskian is always 0. If they are linearly independent, then the Wronskian is always non-zero. So this is really what we're looking for. We hope for a non-zero Wronskian so that we can conclude linear independence. And finally here, finishing off theorem 3, it says, Suppose we have n linearly independent solutions. So emphasis there on linear independent. And we're assuming that P of t is continuous, then any solution whatsoever, any solution of x of t can be written as a linear combination of those n functions. So again, this is just a repeat of chapter 3, but now in higher dimensions. Now we're talking about systems rather than a single differential equation. All right, so let's take a look at our last example for this section. We want to first verify that the given vectors are solutions. Then we want to show that those solutions are linearly independent. And then finally, we want to write out the general solution. So let's start by verifying these solutions. And what I'm going to do is I'm going to verify each of these solutions independently. So I'm going to handle x1, x2, and x3 all separately as I go. So let's take a look at the first one. Remember what it means to be a solution. It means if you plug that solution into this differential equation, or in this case, this system, then it satisfies it, meaning the left-hand side is equal to the right-hand side. So let's compute the left-hand side. So x1 prime is going to be, maybe I'll write it this way, the derivative of this matrix, which is a 2e to the 2t, 2e to the 2t, and 2e to the 2t. So you'll notice all I did was distribute this e to the 2t into each piece and then take its derivative. So this is a little prime notation. This is the left-hand side. Now let's take a look at the right-hand side. So the right-hand side is the following. I want to take that coefficient matrix, 0, 1, 1, 1, 0, 1, 1, 1, 0, and I want to multiply it against x1. So again, distributing that e to the 2t in everywhere. We are going to do vector products, right? The scalar products. So I take this row times this column, and I take that dot product. So I get 0 plus e to the 2t plus e to the 2t gives me a 2e to the 2t. All right, so now I want to do the same process, but with the second row. So I get an e to the 2t plus 0 plus e to the 2t gives me a 2e to the 2t. And then of course, we can do it one more time with the bottom row, and we're going to get the exact same thing back out, 2e to the 2t. So what I have showed is that the left-hand side equals the right-hand side, so x1 is in fact a solution. We're going to do this exact same method for the other two solutions. So let's find the derivative of x2 prime. So that's going to be the derivative of e to the negative t, 0, and negative e to the negative t. And so we get this derivative. And so now let's move on to the right-hand side. I want to take the coefficient matrix times my function. And let's see what we get out. So I get a 0 plus 0 plus negative e to the negative t. For the next row, I get an e to the negative t plus 0 minus an e to the negative t. So that's actually going to 0. And then in the bottom row, I get an e to the negative t plus 0 plus 0. So yes, that does in fact equal that derivative. So far, so good. So let's check the last so-called solution. Checking its derivative here. We want the derivative of e, nope, that first one is 0. Derivative of 0, e to the negative t, and negative e to the negative t. All right, so we want to find this derivative. So that would give us 0, negative e to the negative t, and e to the negative t. All right, and now checking the right-hand side, I'll copy my coefficient matrix. Multiply it against x3. And see what we get out. I get a 0 plus an e to the negative t minus an e to the negative t, which is going to cancel. The next row, I'm going to get a 0 plus 0 minus e to the negative t, and a 0, e to the negative t, and 0 again. All right, so it's checking out. So we have officially verified all 3 solutions. So now let's go back up to the problem statement. Verify that the given vectors are solutions of the system, check. Then use the Wronskian to show that they are linearly independent. So remember, the Wronskian is defined to be the determinant of the matrix whose columns are the solution vectors. So I want to take x1, x2, and x3 as column vectors and stick those in the column of the Wronskian and then compute the determinant. So let's do that here down below. So the Wronskian in terms of t will be the determinant of e to the 2t, e to the 2t, e to the 2t. There's the first column. The second column is e to the negative t, 0, negative e to the negative t. And then the last column is 0, e to the negative t, negative e to the negative t. I would like to compute this determinant. So I'm just going to go ahead and expand along the top row. So I'm going to get my negative 1 to the 1 plus 1, e to the 2t, times that cofactor matrix. So if I strike through, I get 0, e to the negative t, negative e to the negative t, and negative e to the negative t. And then my next term is going to be a negative 1 to the 1 plus 2, e to the negative t. Let me clean up these lines. And what was that? That was an e to the negative t right there. And now if we strike through that row and column, our cofactor matrix, I'm going to squeeze it in over here. Oops, I want determinant, so let's do straight lines. Is going to be an e to the 2t, e to the negative t, e to the 2t, and negative e to the negative t. All right, and so what we want to do is we just want to flesh out this determinant here. So we get an e to the 2t times 0 minus a negative or plus an e to the negative 2t. All right, and so then the next term is going to be a minus e to the negative t. And this determinant is a negative e to the t minus e to the t. And so when it's all said and done, what are we getting here? We are getting e to the 2t times e to the negative 2t is e to the 0 or 1. And then I have a negative e to the negative t times negative 2e to the t. And so this becomes 1 plus 2, which is 3. And of course, 3 is not equal to 0. So I'll put a check mark here to say this indicates that these solutions are linearly independent. And now we just want to write out our final solution, of which I totally don't have enough room to do, but we're going to squeeze it in here if we can. So let me come back over here, and my solution is vector x of t equals. All I want to do is I want to take a linear combination of these vectors. So if you're looking back up here at the Wronskian, I'm just going to take each of these rows and add them together with C1, C2s, and C3s. So I get a C1 e to the 2t plus C2 e to the negative t, and then we would have a C3 0, which I won't write out. We have a C1 e to the 2t, a C2 0, and a C3 e to the negative t. And then finally, across the bottom, we have all three terms, C1 e to the 2t minus C2 e to the negative t minus C3 e to the negative t. Pretend that is just one matrix bracket there, just ran out of room. So this x of t right here is your general solution to the system of differential equations given above. All right, that was a workout. So we're just going to end here with a theorem, a statement of a theorem, and it's referring to non-homogeneous systems. So this last example was homogeneous. Again, to remind you why is because we did not have any plus f of t functions. So there were no external functions here. If you have external functions, how you handle that is the same way you handled it back in chapter 3. So we're going to let xp be a particular solution of the non-homogeneous linear equation. So again, we're talking about non-homogeneous with our f of t function. We're going to assume that p of t and f of t are continuous. If you have these n linearly independent solutions of the associated homogeneous, then what you're going to do is you're going to take the linear combination of those linearly independent solutions and you're going to tack on your particular solution, and that's going to be your new solution. So again, it's just going through that complementary function plus the particular solution to get your general solution. So this concludes section 5.1 over matrices and linear systems. And then we will continue on in chapter 5, learning about how to not only find these particular functions and these linearly independent solutions, but how to utilize linear algebra while we're doing so.